In this video, we will talk about what level surfaces are. So I want to begin with an example. Let's suppose that we are looking at the function f of x comma y comma z equals x squared plus y squared plus z squared. So this is now a function of three variables. A function of three, I'm just going to say, I'll abbreviate vars. That just means variables, because I'm inputting values for three variables, for x and the y and the z. So using our same idea from functions of two variables, we could let our function, we could call it a new variable for the output. I'm going to let w be the output, so it's going to be f of x comma y comma z. And if we do that, we get the equation w equals x squared plus y squared plus z squared. So because this equation has four variables, the graph is four-dimensional. This graph is going to be four-dimensional. It's going to exist in x, y, z, w space, in a four-dimensional space. But we can't visualize four dimensions, so we can't graph this, unfortunately. So we can't graph this. I'm going to put a sad face. We're bummed out. We can't graph this. But we can draw what are called level surfaces. So we can draw what are called level surfaces, even though I won't be able to draw the whole four-dimensional graph. So what is a level surface? It's similar to a level curve, but talking about three variable functions as opposed to two variable functions, or like we did for level curves. So a level surface of a function of three variables, f of x comma y comma z, is a surface of the form where my function f of x comma y comma z, I set that equal to c, where c is a constant. So when we do that, when we set our three variable function equal to a constant, we're going to get an equation that has three variables in it, x and y and z. So that graph is going to exist in three-dimensional space. So that is something that we will be able to hopefully draw, assuming it's something that's simple enough. All right, so let's look at an example. Suppose that we have the function g of a comma b comma c equals ln of c minus a squared minus b squared. Let's find the domain of this. So remember, to find the domain, I need to think about what the restrictions are on the inputs. So the domain has to do with the possible inputs. I need to think about, are there any restrictions that limit my inputs? So pause the video for 1 minute and see if you can identify what any restrictions there might be here. So 4, 3, 2, 1, pause that video. Pause it for a minute and just try to identify what the restrictions are here. So this is a good algebra exercise, identifying restrictions based off of the type of function I have. All right, so hopefully you've tried that for about a minute. Let's talk about it together. So I see one restriction here. With this ln function, the inside of ln, which is c minus a squared minus b squared, the inside of ln has to be greater, strictly greater than 0. No equal sign. I can't even plug 0 in to ln. So if we isolate for, I think it's easiest to isolate for c. We'll get c is greater than a squared plus b squared. Okay, so to graph this, it might be helpful to graph c equals a squared plus b squared. Okay, so when I draw my axes here, I'll have c, a c-axis, an a-axis, and a b-axis. So those are my variables here instead of x, y, and z. But c equals a squared plus b squared, that's just a paraboloid. That is a paraboloid. In fact, we've seen that earlier in this section's videos. Okay, so if I draw this paraboloid, I need to keep in mind that c is going to be greater than a squared plus b squared. which means we got to make the paraboloid dashed. So that means I'm not allowed to be exactly on the surface of the paraboloid. Maybe I'll get to be inside or outside, we'll figure it out. But I'm going to draw like a dashed. This isn't just a parabola, it's a dashed 3D paraboloid. So even like the curvature nature of it is all dashed. Okay, so because c is greater than a squared plus b squared, that means we're not allowed to be on the surface of this paraboloid. It actually might be a little bit better if I draw this dash for the back. It looks a little bit more 3D. So because c is greater than a squared plus b squared, that means the z values, or I guess c values here, need to be higher up. So that means we can be anywhere sort of like above and inside this paraboloid. So our region, our domain, is the interior of the paraboloid. Ooh, that's not how I spell it. Paraboloid. C. Let's erase that. C equals a squared plus b squared. So the interior of it. Okay, so that is my domain. Next, let's find the range. So to find the range of this, we had an ln function. So let's think about what the range of ln typically is. If I have ln of x, one variable function, this is range all real numbers, or in interval notation, it's negative infinity to positive infinity, thinking about the graph of ln of x. And in my equation, if we by letting a and b both be 0, we can see that the inside could be whatever we want. Because now we get ln of c, and on its own, let me write that better, ln of c, which still takes on all real values. Okay, so because of that, the range is still negative infinity to positive infinity. So there wasn't anything about this function that sort of limited what the range would typically be from an ln single variable function. All right, so finally, let's talk about some level surfaces. Let's describe the level surfaces. Okay, so this doesn't specify what I'm going to let that c value equal, so I got to be more general. Let's let our function ln of c minus a squared minus b squared. I don't want to call it equal to c because I already have a c in my problem. Let's call it k. Let's pick a different variable. So let's choose a different variable since we already have c in this. All right, so now let's transform this to get it let's transform it to get it in exponential form. So if I rewrite an ln in exponential form, I'll get an e in there. And the exponential e to the whatever, that this is in the inverse of ln. So it'll switch the inputs and the outputs. So the output of this ln is now the input in my exponential function. So I put it here. That's typically where the x would go. So the output of the ln becomes the input of the exponential. And the input of the ln becomes the output of the exponential. So I'll get c minus a squared minus b squared out here. All right, so we have this. One simplification that we can make is k is just a constant, which means e to the k is going to be a constant. So let's just rename this constant. Let's call this just d. And e to any real number power is always positive. So d is a positive number. And doing this will just simplify what my equation looks like. Now I get d equals c minus a squared minus b squared. And like before, let's isolate for c. We'll get c equals a squared plus b squared plus d. Okay, so my level surfaces have this form. In the shape of this graph, keep in mind that d is just some constant, it's just some positive number. This is an elliptic paraboloid. So elliptic paraboloid. Okay, it's an elliptic paraboloid that's been shifted. That's what the d does. It's been shifted, and d is a positive number, which means it's been shifted up by d. And d is a positive number. Okay, so let me draw one specific example. So for example, what if we let k equal 1? So if k equals 1, then we end up getting e to the k, which is just e to the 1, equals c minus a squared minus b squared. Okay, so I'm setting my function equal to 1 here, k equal to 1. All right, so now if I isolate c, we get c equals a squared plus b squared plus e. Okay, so now if I draw this paraboloid, so I'll draw my axes, draw some axes, a and b and c, negative direction, and one more negative direction. So my paraboloid has just been shifted up e units. So the vertex now is going to be at 0, 0, e, but it's still an upward sort of facing paraboloid. So I still got something like this. And if I were to draw a cross section would look like this. And this is actually a circular paraboloid. The cross sections are circles in this case. So what does this level surface mean in terms of our function? So what this particular level surface means, well, we set k equal to 1. That means if we were to take any point like this that's on that surface, all the points on this particular level surface, so this is the level surface from setting the function equal to 1. When you plug these points into the function, they get sent to the output 1 by the function. So that's what this level surface represents. If I take any point on this paraboloid, and if I were to plug that into my function, if we were to plug that in to this function, plug in the a value, the b value, the c value into here, the output ln of that whole thing should be 1. And I can't draw a graph of that whole thing because I would have to have 4 variables, and that's 4-dimensional, and I can't draw stuff in 4 dimensions. So the best that I can do is I can think about what these level surfaces look like. The level surfaces will at least describe all the points that get sent to a particular output. All right, so finally, in terms of our goals, we have completed our last goal for this section, which is talking about what level surfaces are and how we use them to visualize functions of 3 variables.